An on-off controller, or signaler as they're sometimes called, will set its output so that it increases the process whenever it is below the set point. It then changes its output to decrease the process if it rises above the set point. In a typical heating application, something called reverse action is used. In this way, the heating output is turned on when it is below the set point and it is turned off when it is above. Most people are familiar with this concept as it's exactly the same as is used in their home thermostat. For a cooling application, direct action is used. In this case, the output is turned on whenever it is too hot and turned off whenever it is too cold. A proportional controller doesn't just turn its output states to on or off, it can adjust them anywhere between 0 and 100% of available power. The direction of output is still important with proportional control. With reverse acting, the process is slowly moved from 100% through to 0% as the process rises. With direct acting outputs, the process will move from 100% to 0% as the process falls. If the process is properly tuned, the output power from the controller will precisely match the requirements of the process and therefore achieve completely stable control. This is something that's not possible with on-off control. With on-off control, the output will always remain on until the set point has been reached, at which point it will turn off and will remain off until the process has fallen back below the set point, at which point it will turn back on again. This will inevitably lead to some kind of overshoot and undershoot. The amount of oscillation in the process is entirely dependent with the speed at which the process rises and falls. The user has very little control over this except to adjust an on-off differential or hysteresis parameter if available. The on-off switching differential is the distance between the on point and the off point as the process crosses the set point. It is at least one least significant digit wide, which is normally either 0.1 of a degree or 1 degree, but can be adjusted to a wider amount if appropriate. Setting the differential too wide on the process will lead to an extra amount of oscillation up and down, but can be useful to help prevent excessive wear in the control output device, such as a valve or perhaps a contactor or relay. The user has to compromise between good control and the life expectancy of the components in their process. The use of proportional control adds stability to the process and allows the user to control how often their output devices, such as relays and contactors, will switch. Many users are confused by the fact that proportional control can be used with relays or solenoid valves, devices that can only ever be on or off. How is this possible? It's certainly the case that these devices can only ever be on or off, but they can be on or off for part of the time. For example, being on for 50% of the time equates to 50% of power. If the user set a cycle time of 8 seconds and the output was on for 2 and off for 6, this would equate to 25% of power. Similarly, if the cycle time was set to 64 seconds and it was on for 16 and off for 48, this would also be 25% of power. However, the number of switching cycles would be reduced considerably, so you can see how the user can control how often their devices are switched. It might seem that a long cycle time is always good, as it reduces the amount of wear on the mechanical devices in your process. However, a long cycle time is not good for control. If you set the cycle time too long, the process will begin to oscillate, a bit like it did with on-off control. In fact, if you see the process oscillating with the same time period as the cycle time, it's a good indication that you set the cycle time too long. As with many aspects of process control, compromise is needed. It's generally better to set the cycle time as long as you can get away with, but still have adequate control in your process. The exception to this is if your process is entirely solid state in nature, in which case you can probably set the cycle time much lower. We've seen that proportional control will give better stability in the process, so you might wonder why anyone would ever use on-off control. A proportional controller must always be tuned to the process, and this can be a little bit daunting for users. If the process doesn't require a high level of stability, the simplicity of on-off control can sometimes be attractive. Unlike proportional control, on-off control only has as a maximum one parameter to adjust. This is the on-off differential. There are some processes where it is not appropriate to use proportional control. For example, if you have a refrigerator and you're switching the compressor, you would have to use on-off control. A compressor cannot be turned on and off frequently, as would happen with proportional control. Even if the cycle time was set long, it would still switch more often than would be desired. For example, if you set your cycle time to 200 seconds, at 5% of power, the output would only be on for 10 seconds. And at 95%, the output would be off for 10 seconds. Neither would be good for the compressor. In general, if stable control is required and other factors don't prevent it, I would always use proportional control. In fact, there are some applications where on-off control cannot be used. For example, if your controller had an analog output, such as 0 to 20 mA, perhaps for a modulating valve, proportional control has to be used. A modulating valve is driven by a motor and sometimes has circuitry to accept an analog signal to drive the valve. For example, a 0 to 20 mA signal may be taken into the valve where 0% would represent fully closed position and 20 mA would represent the fully open position. At 10 mA, the valve would be half open, 50%. Compare this with a solenoid valve, which can only ever be open or closed, and therefore has to be used with either an on-off output or a time-proportioned output rather than a linear.